Well, good afternoon, which is gonna be good after lunch. And what is the mission after lunch? Not to take a nap. And we will try to work on that. Failure analysis. Post-mortem. So it's better that we begin with what is failure? Many different meanings to the word failures. If somebody fails, he hasn't have a success. If a component fails, it has not fulfilled its mission. And then, after failure, we cannot say, well, it failed. But we have to ask ourselves, why this component failed? Are we able to really understand? In some cases, it is straightforward. In other cases, may be complex. And those like you who have been standing 3 half days talking and talking on fracture mechanics, you have surely learned that a component fails because the applied K was over the fracture toughness of the materials, the K1C. But what is behind this fact? Was the K1C wrong because the component wasn't treated properly? And then many questions arise. We will begin with overload fractures, and then we'll go in the most difficult, sometimes, fatigue fractures. When we speak of fracture modes, in this term, we don't speak of mode 1, mode 2, or mode 3 that you have been learning in the previous lectures. We are speaking of ductile brittle fatigue. And that is strongly influenced by the crystallography. The modes that the atoms are arranged in space. We are all looking at the European Soccer Championships, and we know the different modes of putting the players on the field. 3-5-2 is the Italian mode, but it is maybe 4-1-4-1. The more the players are together, the more difficult it is for the other team to overcome and cut through them. Well, think of the way the atoms are arranged in space in a little bit similar ways. FCC, face-centered cubic, is a way in which the atoms are together very compact. But that does not only mean that they are gonna fail, they are compact in all the directions. And here we will have a ductile microvode coalescence mode at all, I'm trying to find, at all the temperatures. On the other hand, hexagonal closed packed, they are compact, but they are not compact in all directions. And that's why they fail in a brittle cleavage mode at all temperature. And the BCC, the body-centered cubic, are the ones that may fail in a brittle or in a ductile mode, depending on the temperature. And sometimes they fail in a ductile way, but with very low absorbed energy. Let us think of a very simple steel, a carbon steel, which may be a low carbon, 0.15 percent carbon, a middle carbon steel, 0.45, and finally a high carbon steel, a eutectoid steel, carbon content in the vicinity of 0.85. They all show a variation of the fracture mode. At high temperature, they reach the maximum absorbed energy. And when we go to higher carbon content, no matter if the temperature, the absorbed energy is always low. But they may fail in a ductile or in not a ductile mode, in a brittle mode. What's the clue? The clue is the temperature. If you are below a certain temperature that moves to the right as the carbon increase, you are at the brittle end of your fractures. When you are right of this temperature of change, then you are in the ductile end. But also the structure plays a role. Let us see C45R. R means furnace annealed. You can see that the difference between the level of absorbed energy is low at all the temperatures. It's a double at the higher temperatures, but it's a double of a little energy absorbed. So even the double of a little quantity is little. But if you change from R to S, so from furnace annealed to spheroidized, then you see that the maximum level, the upper shelf, that is the way it is named in fracture, the upper shelf absorbed energy is much higher. Why? Because the cementite that comprises the perlite is no more under the form of platelets, is in the form of spheroidized carbides, and all around there is ferrite. So these are 1970 steel, but even nowadays, if you take a new tectoid steel, you have a difference, but very, very low in the furnace annealed stage, and almost no difference in the normalized state. So we are slowly taking the measures of the fracture modes. And we'll see later that fatigue fractures are much more difficult to understand, especially in complex microstructures. Everybody is familiar with cleavage. What is the cleavage? Is a separation of planes of atoms, one from the other, in the direction perpendicular to the planes, which is to be considered as opposite to the slip of one plane over the other. If you have a slip over a plane over the other, you have a deformation. If you have separation between two planes, then you have a fracture. And fracture along a cleavage plane, which is different according to the metal that you are considering. In the case of steels, the cleavage plane is the 100, which is the plane where the body-centered metals is the plane where the frequency of atoms is less. And so they attract one to the other less than in other case. This is ferrite, pure ferrite, which is, as you can see, is a very low carbon because it is polycrystalline iron fractured at a very low temperature, 78 K. So we are for sure in the brittle mode. And we have a little carbide from where the stress built up, and then the fracture propagated in all the different directions along planes, and you have only some small sign that pinpoint to the fact that the plane, the individual plane, is not the same in all the grains. And then you have little difference in the position in space, and the last fracture is a shear fracture that breaks the remaining ligament, the little remaining ligament between plane and plane. You are more familiar to what, when we speak of cleavage, on what is termed as the delta river pattern. You know, a river can go into the sea with a delta. And this is an inverted delta, because let us consider this case in which we have a boundary. And this is the cleavage plane in the previous crystal. And then, as it crosses the boundary, you have that it distinguishes itself in little plane facets. Why is that so? Because when we have a crystal, the next crystal has not the same orientation in space. And then you have that the cleavage plane in one crystal intersects the other crystals at an angle. And so the different cleavage planes in the other crystals are activated first. If you do not understand that, I hope that you all know what's a deck of playing cards. And you have two decks of playing cards slightly tilted, one in respect to the other. And fracture goes between a card and a card in one crystal, and then begins to progress into the other crystal, activating a plane of cleavage on different cards that are parallel to each to the other. Then nature tries to go to the less absorbed energy ever, and then as the fracture progresses from the boundary into the bulk of the other crystal, since each of these steps, which is a shear step between a cleavage plane and the other cleavage plane, and that is an energy absorbing mechanism, then nature tends to reduce these steps into taking the fracture into single larger facets, and the shear steps become larger, but each one absorbs less energy than the multiple ones that you see at the boundary, passing from one crystal to the other crystal. And then you have that this delta reduces itself to a main direction, that is the delta river pattern. And even if you are going not from a grain to another, but from a subgrain to another subgrain, you have similar way of behaving. And that is simple. That is what you see in a monophasic steel. When you have another type of monophasic steel, but with crystals, much more or less, like in the case of martensite, the process is more complex. It is called quasi cleavage. Why is that so? You see, this is a cleavage facet. This is an enlargement of this position, but you see that there are some little holes. These little holes absorb energy. They come from the cohesion of the matrix, metal matrix, from small non-metallic particles like the one that you see over here, and we see it later with much more details in the real ductile fracture. If you compare this type of fracture with this type of fracture, just by looking, you imagine that the fracture is preceded by a much larger absorption of energy, deformation energy, because this surface is not straight. And that can go to an increase of fracture toughness of even 10 megapascal squared root of meter, which is not a mechanism of increasing the fracture and increasing the ability of a metal to withstand stresses, because we are passing from 35 to to a maximum of 45 megapascal squared root of meter. And even 45 is termed very low to be safe. But since we are approaching a way of assessing approximate fracture toughness from the surface that you see, and then to have this you have to use the scanning electron microscope, SEM, because it has got a depth of focus much higher than optical microscopes, then you can see the amount of absorbed energy that goes in the formation of these little holes. But the predominant mode of fracture is a cleavage. It's not completely cleavage, and that is termed quasi cleavage. Now, we have to see these photographs also with the mechanical engineer point of view. And you can see that if the fracture is on this plane, which means that the maximum principal stress is perpendicular to the main fracture surface, and it broke by mode 1 separation into the direction perpendicular to the fracture surface, you have also the action of other perpendicular stresses, because you have always a tridimensional state of stress, and also the other two were strong enough to cause an initial separation along these were the boundaries of the previous austenite crystals, because this steel, which is a 4340 steel, 0.4% carbon, 175% nickel, 1% chromium, 0.2% molybdenum, that was austenitized at a very high temperature, 1200, to enlarge the grain size. Troppo gentile. Very kind of you. But it depends also from the root radius, the amount of stress that you are concentrating in the vicinity of the tip of the fracture. And in the same steel, step quenched from 12 degrees C with less stress concentration, you can have what it is, an overload. So it's always, we are still speaking of overload, intergranular fracture, and the fracture is along the previous austenite crystals. But then the steel was quenched and not tempered, so there is martensite that was formed, and so along the boundary of the previous austenite crystals you can see the facet that refer to the martensite plates, martensite lats that form the actual microstructure. Because if you take a steel, take austenite, then you quench it, it goes into martensite. But yet, this is a steel which tends to have a little bit of a plastic deformation before fracture. And you can see here a small void, a micro void, that formed by decohesion from a previous second phase particle, non-metallic particle. Why do you see it is a non-metallic particle? Because you see that it is much more glowing, because it absorbs electrons and does not conduct them to the bulk of the material. And so you can say that this is a non-metallic particle. And you see, we are speaking of these tiny microvoid that went into here and absorbed a little bit of energy. This is a real microvoid. This is a similar steel that was quenched and tempered at 550, 600, 650 degrees C. So it was quenched and tempered in the usual proper way. How did it fracture? Again, the main mechanism in this case, whereas before we were seeing cleavage, then we were seeing intergranular. Now we are really seeing a ductile fracture by microvoid coalescence, microvoid generation, and then microvoid coalescence. So the first event is microvoid generation. What's the difference between a non-metallic and a metallic particle? A non-metallic particle does not deform. It breaks. A metal instead deforms before breaking. And how does it deform? Deforms by multiple slips in various directions along planes of maximum density of atoms. This is the non-metallical initiating particle. And in the beginning, all this material was around the non-metallic particle. Then, before breakage, we put into that energy. We caused strong deformation of the metal matrix around the non-metallic particle. And here you see the signs of the multiple slips of the various metallic planes that were detaching from the non-metallic particle. And this type of surface is a surface generated by deformation with all these lines in all the directions, which this surface is much more different between the surface around the microvoid that comes from another mechanism, the mechanism of microvoid coalescence. So you have, first of all, microvoid generation. And here you can see that the plasticity within the metallic material was much more than the tiny holes that we were seeing before. You have a relatively bigger hole because the amount of plastic deformation that took place is much more. And then you have to have these micropores coalesce into a complete fracture. Let us suppose that you have copper, oxygen-free, high conductivity copper, which is one of the most ductile material ever. What you have? You have a ligament between the two poles, and you stress the ligament with a stress that causes plastic flow. And by continuing plastic flow, you have that the ligament reduces its size more and more, up to the point that there is no more a ligament, there is no material that is resisting. And this is the limiting of ductility. Think of the amount of energy that goes into this type of mechanism, because it deforms and deforms and deforms, the pores enlarge, 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 up to a single point. But this is only in the case of very, very ductile alloys. In most ductile alloys, the mechanism is another limiting case, the formation of bands of shearing instabilities. That is really a problem. Riuscire a inquadrarmi è difficile perché mi muovo un po'. Ok. What's a shearing instability? It's a mode 2 fracture, because the two sides around this shearing instability behave as rigid bodies sliding one against the other like in here there was a tiny veil of lubricating liquid. You have no more extension in this direction. It is a situation of zero extensional strain. Only shear is a situation of pure shear. And the two pores are connected. This is an extreme. So this is the most ductile case. This is an extreme, pore generation, and then shearing instability. And there are obviously various stages in between. And sometimes you see that prior to the development of the instabilities, tiny micropores may form around the carbides that are present in the matrix. That is what we are going to see. This is a similar nickel chromium molybdenum steel 0.4% carbon, quenched and tempered at 550 degrees C. And here you see the non-metallic inclusion that generate the previous voids, and then the ligament between them mostly fails by shearing instability with some small nucleation of carbides. How do we assess the fracture toughness of these material? Well, these materials for sure is not on the brittle side, but on the ductile side we have to choose between 70 and 100 and 110 megapascal squared root of a meter. And we are here in the low end, around 70, 75, because there is not too much energy that is consumed in the development of these fracture, much more, obviously, than the cleavage that we were seeing before or the intergranular that we were seeing before, but still not too much. And instead, if we go to a 600 tempered martensite, 600 degrees tempered martensite, you see that the surface is more dotted by tiny microvoids that are nucleating between the first ones that are nucleating around non-metallic inclusions. And these are nucleating around carbides. And then you are increasing here the fracture toughness. You are taking it to close to the 100 megapascal squared root of a meter. And if you go further in tempering temperature, almost close to the maximum, you see that the situation shows more micropores, and you go towards the maximum of the range of fracture toughness that we were saying before, 100, 110, 120. It depends much more in this case from the size of the component. If it allows you to have full plane strain, or if it is not large enough and you have some plane stress. Each of the carbide can nucleate one such micropore, and so during tempering you nucleate spherical cementite carbide, and that try to activate micropore formation around them. And so you think, I know everything. I have seen brittle cleavage, I have seen brittle intergranular, I have seen ductile microvoid coalescence. There is another type of ductile fracture that is rarely shown around. We have begun to speak of shear instabilities before, but we have to consider that shear instability is a common way of initiating a fracture in quenched and tempered steels when you do not have a sharp crack, but you have a notch with finite root radius. Now, this is what we were able to show in the case of totally martensitic steel, but that is not very different from the case of quenched and tempered steel. Why is that so? if the strain hardening exponent, think of the tension test, you have the elastic side, then you enter into the plastic deformation region, and this plastic deformation region is characterized by the strain hardening exponent, which for the low carbon steels is in between 0.25 and 0.30. If you go to a quenched and tempered steel, the strain hardening exponent is less than 0.1. And so the material does not generate dislocation and dislocations. And so it may give rise to this type of shear instability fracture. And we'll spend the next 10 minutes speaking about that. What I want to show is these are slow bend tests on Sharpie type specimens with varying notch root radius rho. And you see the rho goes to very little, 0.006, to very large, 1 millimeter. So you are, what's the root radius of a Sharpie specimen, Sharpie V specimen? 0.25. So we are going from much less than 0.25 to much more than 0.25. And if you begin at 0.1, 0.15, you have a fracture along shear instabilities along slip line. What's a slip line? You have to think of a bending test, and the notch. This is the notch. This is the straight line where you have the two acting reactions, and then you have down here the acting force. So you have a slow bend test. And fracture does not initiate along the center line, but at some distance from the center line, it goes along the shear lip that we were seeing before on the fracture surface. So before we were looking in this direction, and this is the final fracture along the notch center line. This is a very much energy absorbing mechanism. So again, we are looking at the notch. This is the notch before fracture. There is deformation of tiny microclaps that are evidenced here by the nickel cladding of the broken surface to better see it. And they generate a stress-free zone at the root of the notch. And then you have the development of a slip line field. Under your opinion, these lines are crystallographic dictated, or are they dictated from a mechanical continuum field? I know that you were sleeping, so if I begin, they are dictated by a continuum mechanics situation. There is nothing of crystallographic. These lines are transparent to grain boundaries. They are transparent to inclusions. Some tiny holes may form before the activation of the shearing instability, but once the instability goes along this line. If it is not dictated by the structure, the internal defects, then the solution that takes you to the activation of one of these lines or the opposite one that has the same geometrical features is a chance. So you can have a fracture along this line, which is a logarithmic spiral, or the corresponding one on the other side. And in the same specimen, you may have fracture that begins one side or fracture that begins one side. And you may have fracture along one of these lines and fracture along the intersecting line of the opposite fan, and again going back. And in fact, this is what we see. What happens along one of these slip lines? We have to have a plastic zone, first of all. This is a plastic deformation mechanism in which there is no extensional strain. This component is equal to this one. But along this line, the two sides, again, they act as rigid bodies that slip one over the other with a different velocity. And so you have, in the case of weak instabilities, just a movement in this direction. In the case of strong instability, you can have fracture. And here, this is the copy of a slide that was on the 180 degrees rotated along the main axis. What I wanted to show you, this is the original notch. This was a very large piece of material that was subjected to bend in order to have the possibility of make photographs of not a broken material. And you can see the initiation of a tiny crack along a slip line, and you see that the two sides moved, one in the direction, the other in the other direction, in a different way, in order to create a step on the surface. So when the notch root radius is almost nil, then there is no shear lip. You have just a tiny series of micro cracks that dot the surface. When you go to a larger notch root radius, you see slip lines that follow different types of the fun of lines that we were seeing in green, and you see that there is the activation of many of these slip lines. You increase the notch root radius, then you increase the size of the slip line because you are going farther to the right or farther to the left in respect to the notch center line. Think of the green view that I was showing before. Larger and larger shear lips. But why do I say that is a very, very energy absorbing mechanism? Because you have a fracture along a predominant slip surface whose intersection with the plane is a logarithmic spiral. But within this piece of material, you have slip along each of those surfaces. And so the whole material between this one and the corresponding line on the other side is deformed. So even if the final situation, the final surface seems smooth, the mechanism of plastic deformation that goes on below that is much, much, much intense. When you have a rho equal 1, you have a monster of a slip line that can be seen with the naked eye. You see, this is 0.1 millimeter, which is the possibility of seeing with your naked eye. You can distinguish two lines different from one to the other with a naked line if they are distance one from the other of at least 0.1 millimeter, a tenth of a millimeter, and then it is 4/10 of a millimeter, so that you can see it with the naked eye. So to summarize what we have been seeing before, the way I should be like the goddess Kali with 4 arms to keep the microphone. Tanto questo non va. Allora, summarizing. Brittle fracture. They can be of the cleavage type or of the intergranular type. Think that you might have a combination of ductile and intergranular, but then it becomes too a difficult consideration. We have to have some categories. Brittle cleavage, brittle intergranular. Then we have ductile fractures that can be, most of them, by microvoid ductilation and microvoid coalescence. Some of them can be of the shear instability type. Shear instability is under shear stresses, and so they are what in fracture mechanics are termed mode 2 fractures, because there is no separation in the direction perpendicular to the surface, but separation in the direction parallel to the surface. And so this is the complex of overload fractures. But overload fractures are usually preceded by fatigue fracture. And now, when we perform failure analysis, we would like to know if the real cause is overload or fatigue followed by overload. And so we have to understand fatigue fractures. Now we'll see simple fatigue fractures, and then we'll go into more complex fatigue fractures, the ones that are difficult to assess. As I was telling you, when you have a monophasic alloy, then usually it may be that the possibility to assess that there was a fatigue fracture is straightforward. Now, what really characterizes fatigue fractures? The feature that most characterize fatigue crack are what are termed striations. And I show you just after. These are striations, and you have to look at it in the scanning microscope at very high magnifications. But in ductile materials, you can have microvoid, coalescence, and in brittle materials, under the case of fatigue, you may have cleavage, microcleavage, quasi cleavage, or intergranular fracture. So usually the failure analyst is confident to be able to recognize fatigue fractures. Confident. Oh, I will see, and I will tell you if it is or not fatigue. Because he thinks of striations. But instead, he may have fatigue fractures characterized by cleavage, by intergranular, or even microvoid coalescence. Let us look at the upper figure. You see striations, but think of these macrovoid nucleation around spherical particles. Let us consider that before fracture by fatigue or by something else, you have a crack. If it is a crack propagating by fatigue, it has a tip, and think that at the tip of the crack there is a stress concentration and the generation of a stress field ahead of the tip. That we know that. We have been speaking of that at least in some of the lectures that you have had here too. So, if you have a stress concentration, you have a high stress, and then you are having a plastic deformation zone, and within that zone you may have nucleation of a void by separation of the metallic material around a second phase, usually a non-metallic particle. But here you see the generation of these voids does not obscure the fact that the main mechanism is striations formation. Then we'll see how striations are formed. But this is an alloy steel with about 750 megapascals of yield strength that comes from a nuclear plant. This is the not embrittled condition, and is instead the one that comes from a nuclear plant that was broken by fatigue, but it was embrittled. So, what do you see here? You see intergranular along some striations. So, the possibility of having completely intergranular, because the material, the alloy steel, is completely embrittled, even by fatigue, is possible. And striations can be reduced to very tiny portion or not be seen at all. So remember that striation is not the common, is not always, sorry, I was wrong, is not always the true mechanism that you see on a fatigue surface. For instance, this is a aluminum silicon alloy, this is a cast alloy, this is an alloy that is used for engines, for instance, and when it is tested at 150 degrees C, you see striations. These are silicon particles that are broken, and between this silicon particle and the next silicon particle there is a ligament that is broken by the mechanism of formation of striations. And this is the mechanism of formation of striations. We see the cycle that leads to the formation of one more striation on the fatigue surface used. Begin Fourier count, there are 4 grooves on the side, on each side of this crack. Then you are increasing the stress, you are separating the 2 faces of the crack, then you are more increasing the applied stress, the front evolves, it enlarges in the direction of the crack propagation, forms a completely new front with the maximum deformation acting on this side at 45 degrees, the direction of the maximum shear stress. And then when you go down, you take back the front, but these sides that were most deformed remain. The front of the crack bends back, and then when you go back to another situation of sigma equals 0, you have created a further groove. This is the situation of fatigue, crack growth, and formation of striation. Now, before we go and get a coffee, because I was going to sleep and some of you were following me, we have to think this. If going from here to here and to here and to here, in this zone you find a brittle zone, then the surface changes completely its appearance. Because if you find an embrittled grain boundary, like in the case that we were seeing just before, then you have a jump and the formation of a crack that is bounded by one of that embrittled surface that we were seeing before. And so we stop here. Let's go and get a coffee. I think that